Today on the Deep Dive, we are taking you inside, well, the cognitive architecture of advanced AI.
We're going straight to the source material on something called world models, or WMs.
Now, if you want an AI agent to be competent in any complex environment, I mean, whether it's navigating a building or running a super-sensitive factory robot, it needs more than just, reactive programming.
Right.
It needs an internal map, and this is the key part, a crystal ball.
The crystal ball, I like that.
That internal predictive capability, the ability to anticipate what happens next and act on that simulation, that's the world model.
And it sounds futuristic, but the idea itself has really deep roots. In control theory, we've used dynamics models for decades to describe how a system changes.
Sure.
But I think the most relatable version comes from cognitive science, our own internal mental models.
Oh, like how we think.
Exactly. Every time you plan a route, or you guess how hard you need to push a stiff door, or even just, think about the balance shift you need to ride a bike.
Yeah.
That's your human world model running a really fast, energy-efficient simulation in your head.
So it's the difference between knowing the rules of chess and actually being able to calculate 3 moves ahead.
Precisely.
We've seen such a rapid acceleration in these models lately. What drove this sudden maturity?
It's really a confluence of a few things. We now have these very sophisticated model-based reinforcement learning, or RL, techniques.
Okay.
We have massive, and I mean massive, heterogeneous data sets. Think all the video on the internet.
The fire hose of data.
Yes. And on top of that, incredibly powerful deep learning architectures that can capture really complex nonlinear dynamics.
And the milestone that I think really brought this into the public eye was OpenAI's Sora.
Oh, absolutely.
Watching Sora generate these long videos that just look and feel physically consistent. It's jarring. It suggests this is no longer just theoretical.
It's not. It's maturing dramatically. But that actually leads us right to the mission of this deep dive. While world models are clearly this cognitive engine for AGI, for artificial general intelligence, our sources show a fundamental tension in the field.
A tension, yeah.
Yeah. Current models fall into 2 pretty distinct camps: specialists and generalists. And we need to unpack this trade-off.
Why is that so important?
Because getting to AGI means you have to reconcile both rock-solid precision and flexible, broad generalization.
That sounds like trying to build an Olympic athlete who's also a world-class accountant.
It is. It's a very tough balance.
So let's start with the foundation.
Yeah.
Why is a world model a necessity for AGI, not just a nice to have?
The theory is actually quite rigid on this. Any agent that achieves competent performance across a diverse set of tasks, tasks with complex goals and unknown variables, it must have learned an accurate predictive model of its environment.
Without it, you're just guessing.
You're just doing trial and error, not goal-directed action. You can't be competent if you don't know how your choices change the world.
And practically, what makes this architecture so attractive for developers, especially since collecting data is so expensive?
It's all about efficiency. What we call sample efficiency.
Okay.
So traditional model-free approaches require the agent to interact like thousands or millions of times with the real world to learn one specific task.
Which is incredibly costly.
Really incredibly. A world model flips the script entirely. It uses task-agnostic experience, just watching the world or playing around randomly, to build a reusable internal predictive environment.
I like that. So it builds the digital playground once.
Exactly. Once that playground is modeled, the agent can train for all sorts of goals, infinitely fast, inside that simulation.
Which saves the cost of all those real-world demonstrations.
Right. It makes WMs far more sample efficient than their model-free counterparts.
Okay. That clarifies the need. So let's get into this core dichotomy, specialist versus generalist. If Sora suggests the future is massive general models, why are we still investing so heavily in specialists?
Because specialists are defined by their laser focus. They aim for extremely high precision, but within a very narrow domain.
A single environment, or maybe a few related ones?
Yes. And they get that accuracy by relying on targeted, often hand-engineered priors or very specific, precise data.
Can you give us a tangible example? What does a specialist model look like in the real world?
Think about commercial finite element method simulators like ANSYS or COMSOL. We'd call those specialist WMs.
So engineering software.
Right. The physics laws they use are universal, but to simulate, say, an industrial robot, you have to input precise parameters: the exact mass, the friction coefficient, the material composition.
All tailored to that specific robot in that specific environment.
Exactly. They are built for mission-critical tasks where 99% accuracy is mandatory.
Like assembling microchips or analyzing a load-bearing structure.
Perfect examples. But their limitation is huge.
Yeah.
The cost to build them is high, and they have severely limited transferability. Change the environment, and you have to redesign or retrain the whole thing.
It's a bespoke suit, tailored perfectly for one occasion.
A very expensive bespoke suit.
And on the other side, the generalists. These are the foundation models of the world, aren't they?
Yes, sometimes called World Foundation Models, or WFMs. Their goal is totally different. They want to approximate dynamics across an open-ended distribution of environments.
So, everything.
Sort of, yeah. They're
Right.
massive, trained on huge, diverse data sets. Think Sora, or research models like Unisim and Pandora. Their strength is generalization, zero-shot adaptation.
They inherit a kind of common sense about how things work.
That's a great way to put it. But the trade-off is almost always a compromise on precision.
How so?
A generalist might understand that if you push a block, it moves and it won't go through a wall. But ask it to exert a precise 2.5 newtons of force to insert a delicate pin.
It might fail.
It very well might. It gets the big picture physics right, but sacrifices that fine-grained control. That's why you usually still need to fine-tune them for specific high-fidelity jobs.
So we've got this continuum. Explicit, physics-based modeling on the specialist side, and implicit, data-driven learning on the generalist side. The holy grail for AGI is somehow getting both.
Exactly. And to figure out how to bridge that gap, you have to look inside the models themselves.
The components.
The components. WMs are defined by three things: state representation, action representation, and the architecture. And these design choices dictate where a model lands on that spectrum.
Let's start with state. This is how the AI perceives its environment, right?
Yep. Specialists favor what we call physics-grounded representations.
Okay, what are those?
They're clean, low-dimensional states.
Yeah.
Things like positions, velocities, torques, or if you have contact and collision, geometric representations like point clouds or meshes.
The advantage being they have explicit physical meaning. They're interpretable.
Exactly. It enables very accurate reasoning.
But as we move toward the generalist side, we see a shift to learning-induced states. This is where it gets a little abstract. What are these latent spaces?
Think of it like this. Instead of remembering every single pixel in an image, the AI creates its own highly efficient shorthand notebook.
So,
That notebook is the latent representation. It's a compact, hidden state that encodes only the most task-relevant information. It gives up on perfect reconstruction.
systems like Dreamer, which do these latent rollouts.
Right, they are prioritizing learning the dynamics in that compact space, which is way more scalable.
So the latent state is the AI's best guess at what actually matters for predicting the future.
Precisely. It's a massive efficiency gain. The trade-off, though, is fidelity. If the AI shorthand is too sloppy, if it abstracts away too much,
Then its predictions get fuzzy.
and its ability to model precise physics is lost.
Okay, now for the control interface. Action representation. This seems like a critical point in the trade-off.
It is. It's controllability versus flexibility.
How so?
Specialist models use physically executable actions. These are fine-grained control signals, force, torque parameters, things you need for complex, contact-rich jobs like assembly.
You know exactly what control signal gives you what physical outcome. High controllability.
Yes. But generalists want flexibility and scale, so they lean towards learnable abstract actions.
Which often means just text.
Exactly. Textual instructions. Pick up the blue cup, turn the corner slowly. Models like Sora operate at the semantic level. It's a super flexible, scalable interface.
But that natural language has a hidden danger, doesn't it?
A pretty significant one. Language is inherently vague.
Right.
If you tell a robot, move the box carefully, that instruction lacks the precision of telling it, exert 0.5 newton meters of torque on joint 2 for 100 milliseconds.
In a mission-critical task, that vagueness could lead to disaster.
It could lead to unpredictability and failure. And that's why specialist precision remains so essential.
Okay, finally, let's touch on the architectures driving the generalist side. We know transformers are everywhere, and I'm guessing they're here too.
Oh, indeed. We've seen the rise of transformer dynamics models, TDMs. They're just inherently suitable for this because they can capture long-range dependencies across vision, language, and actions.
Which makes them great for scalability and long horizon planning.
Yep. And another interesting trend is diffusion models.
Like the ones that generate images.
The same core idea. Diffusion world models, or DWMs, are fascinating because they excel at modeling complex, multimodal distributions, the messy outcomes you see in the real world.
They're good at handling uncertainty.
Very good. There's a model called Diamond that used these diffusion rollouts to get state-of-the-art results in really complex Atari games.
And of course, we can't forget the power of LLMs.
No, they act as these powerful pre-trained backbones, models like Genie Envisioner or Cosmos.
How they help?
When you train them on vast data sets of, say, robots moving around, they inherit a wealth of common sense and rich priors about real-world dynamics. It gives the generalist world model a highly educated guess about how the world works before it even starts.
So you have these two excellent but pretty incompatible systems, a specialist and the generalist. They need a bridge.
They need a technical bridge. And this brings us to what might be the most exciting advancement: differentiable physics.
Okay.
See, the primary struggle for any specialist model has always been the sim-to-real gap.
The mismatch between the simulation and reality.
Yes. And historically, simulators like Bullet or Mujoko were non-differentiable. They were a black box.
What did that black box mean for a developer trying to use one?
It meant that if your simulation didn't match reality, if your virtual robot kept slipping but the real one didn't, you had to calibrate it manually.
Some guessing.
Basically. Expert-driven, trial and error. You couldn't use efficient methods like gradient descent because the error couldn't flow back through the physics engine to tell you what to fix.
That sounds like a colossal waste of time and talent.
It was incredibly sample inefficient. This is where differentiable physics is a revolution. The term differentiable means that the gradient, the mathematical measure of error, can flow directly through the entire simulation.
And what does that mathematical breakthrough actually let you do?
It enables efficient system identification. Instead of guessing the friction coefficient, the model automatically infers it by minimizing the prediction error. It uses gradient descent to make the simulation match reality.
So systems like DiffTaichi, Brax, and the newer Mujoko.
Mujoko XLA, yes. They've all proven this is possible, and it leads to huge gains in data efficiency and stable, long-horizon prediction.
But it's still at the state-level position. Velocity. It still needs the AI to know those variables.
Yeah.
How do you scale this up to handle raw images and video like a generalist does?
That is the absolute state-of-the-art breakthrough. GAP-level differentiability, geometry, appearance, and physics. It solves the input problem. It constructs a unified 3D representation, often using NeRFs or 3D Gaussian splatting, that allows for end-to-end optimization directly from visual observations.
Okay, let me zero in on that. You're saying the system can look at a video of an object, and from that video, a single representation captures its color and texture, the appearance. It shaped the geometry and its physical properties like mass and friction, the physics, all at once.
That's precisely right. The gradients flow directly from the pixels, back through the geometry and appearance layers, all the way down to the underlying physical parameters.
So you don't need a separate state estimator module anymore.
You don't. It fundamentally closes that sim-to-real gap with visual data and makes the whole thing dramatically more scalable.
Give us a concrete example of this in action.
The PINWM approach is a fantastic case study. It leverages differentiable rendering, in this case 2D Gaussian splatting, and integrates it with a differentiable physics engine designed for contact dynamics.
Okay, and what can a model like that achieve?
It can identify an object's true physical parameters, its mass, its friction, from just a single task-agnostic interaction video.
Wow.
But then, and this is the crucial part, it uses those identified parameters to create what they call physics-aware digital cousins.
Digital cousins, what are those?
They're simulations where the parameters are slightly randomized around the real-world values it just found.
Why do that?
It compensates for any tiny, unmodeled dynamics that the simple physics engine might have missed. And policies learned inside this highly calibrated but randomized simulation, they can then transfer directly to a real-world robot without any fine-tuning in the real, costly physical environment.
That completely shifts the paradigm. You're taking the specialist's need for precision and making it scalable with a generalist's data stream. You get a perfect digital twin ready for action.
That's the goal.
So, to summarize what we've dived into for you today, world models are this essential cognitive core giving AI that predictive capability.
Yeah.
The field operates on a clear continuum. On one end, you have specialists offering precision for mission-critical tasks, but they don't transfer well.
And on the other, generalists offer broad adaptability, but often at the cost of that fine-grained accuracy.
And the most important trend is the integration of the two.
It is. Techniques like differentiable physics, and especially these unified GAP-level models, are the technical bridges. They let us automatically build specialist quality simulations by analyzing raw video at a generalist scale.
This synergy is what's needed for truly capable AGI.
It is. The pace of progress is extraordinary, but this convergence, it introduces a new and potentially critical flaw, one that's tied directly to the generalist approach.
And that raises an important question for you to mull over. We know that these massive generalist systems, especially those tied to LLMs, are susceptible to hallucination.
Right, spontaneously assisting plausible but factually false information.
So what happens if an AI's internal model of reality, its world model, is a generalist and can spontaneously invent plausible but physically false dynamics?
Maybe it decides a heavy box is suddenly light, or that friction just disappears for a moment. What happens when we prioritize that big picture generalization and scale over verifiable physics-bound accuracy, the ability to fabricate reality internally? That's the critical question we have to answer before we can fully trust these generalist agents in the open world.